In this video, we're going to talk about Descartes' rule of signs. This is another rule that will help us to minimize guessing when guessing the roots of a polynomial, of a higher degree polynomial. Anything helps. If we can narrow down the number of guess trials, the better. So this is another theorem that helps us narrowing down. It says if we let f of x be this polynomial where we have x's to some powers and the coefficients in front of them, and it's a polynomial with real coefficients, the number of positive real zeros is either equal to the number of sign changes of f of x or is less than that number by even integer. Okay, so we will be looking for sign changes in f of x. Okay, for positive real zeros. Now, the number of negative real zeros is either equal to the number of signs changes of f of negative x or is less than that number by an even integer. So again, when we are looking for negative zeros, we're looking for sign changes in f of negative x. Here's f of x for positive and f of negative x for negative. So let me give you an example. Here it says use Descartes' rule of signs to determine the possible numbers of possible and negative real zeros. So we're given f of x, and remember, for positive real zeros, it's the number of sign changes in f of x. So we already have it, and f of x. Let's count the number of sign changes. Now, the first term is positive. The coefficient is positive, and the next one is negative. So there is one sign change right here. Then this one is negative, the following one is positive. So that's another sign change. And then another sign change, and yet another sign change. So this polynomial changes signs basically on every term. Now, important, don't forget to line up your terms from highest power to the least power. It has to be in that order, and then we look at the sign changes. So here we have 1, 2, 3, a total of 4 sign changes. So let's say that possible number of real of positive zeros is either 4 is max, right? But Descartes' rule says it could be less than that by an even integer. So subtract an even integer, the smallest even integer is 2. So subtract 2, we get 2 or 0. So there could be at maximum is 4 and or 2 or 3. So in other words, there could not be 1 or 3 positive zeros. Yeah. Okay, so let's proceed to possible negative zeros. So for the negative zeros, we need to substitute x with a negative x. And what do we get? We get 2 negative x to the 4th. minus 10 negative x to the third plus 11 negative x squared plus minus 15 negative x plus 12. Now let me double check. So plus minus plus minus plus. Okay. Now let's simplify that. Negative x to the fourth is just x to the fourth, so it still is x to the fourth, 2x to the fourth. Now negative x to the third is actually negative x cubed multiplied by negative 10. That's plus 10x cubed. Now here negative x squared is just x squared plus 11 x squared, and here we have plus 15x plus 12. Look at that. 0 sign changes. So this means that this polynomial does not have any negative negative zeros. So no possible negative zeros. So this means that we're not gonna even try, like you know, when we're applying our possible zeros theorem, possible rational zeros. If we have any negative ones, we don't even try them. We try only positive ones. Alrighty, let's take a look at this example. Use Descartes' rule of signs to determine the possible numbers of positive and negative zeros. So again, we have f of x, and we can, so here the first term is negative, the next one is negative, no change there. But from the second to the third, there is a sign change. The second is negative and the third is positive, okay? And then we have positive to negative, so once more, and then followed by a negative. So there's 2 sign changes there. So we're gonna say that there are 2, or remember now the theorem says that it's either equal, the number of positive zeros equals to the number of sign changes, or less than that by an even integer. So it's 2, or the smallest even integer is 2. So subtract 2 from 2, that's a 0. So it's either 2 or 0. Positive real zeros. Okay, now to determine the number of negative real zeros, we we substitute x with a negative x. So we have negative. Now notice that this negative is not under the fourth power, so it stays outside. When we substitute our x with a negative x, this negative stays outside it, is not affected. Okay, negative 3 times negative x cubed plus 6 times negative x squared minus 4 times negative x minus 12. Okay, so let's simplify. This negative is outside. This 4 has nothing to do with it. But negative x to the fourth becomes just x to the fourth. And then negative x to the third is actually negative x to the third multiplied by negative 3 will give us positive 3x to the third. And here negative x squared is just x squared, so we have plus 6x squared plus 4x minus 12. Okay, so how many sign changes do we have here? From negative to positive here, positive, positive, from positive to negative there. So we have 2 sign changes in f of negative x. And so therefore, we will conclude that there are either 2 or 0, again, less than this number by 2, or 4 or 6, you keep going if this number is high. 2 or 0 negative real roots. Real zeros. Okay, so that's easy, but now let's talk about something else. So this polynomial has a degree of 4, and we said that it could have 2 or 0 positive zeros and 2 or 0 negative zeros. Let's actually put this information together. So we're going to create a table for negative. In one way, we're going to have negative zeros. And we also have, well, let's do positive zeros here. Okay, positive zeros. Okay, we also know, I'm gonna make it like leave the empty column for other types of zeros. And what do we know? We know that the total number of zeros should be like, since the power of a polynomial is 4, the total number of zeros is always going to be 4, no matter what. It's gonna, the total number of zeros have to end up to 4. Okay, if we have 2 positive zeros and 2 negative, no problem, right? But what about if we said that there will be 2 or 0 positive. So what if we have 0 positive and the most negative that we have is 2? We need a total of 4 zeros altogether. So which ones are we not including here? And that is complex. So if there are 0 positive and 2 negative, then there must be 2 complex zeros. And complex come in pairs. That's why in Descartes' theorem says it's this is the maximum possible, but then you reduce by 2 the number of possible positive zeros. Same for negative zeros, because if we have complex, they would be by 2, but in 2s. Okay, so for here then, for the first case scenario, we had 0 complex. Okay, what else? What are the other scenarios? We could have 2 positive, 0 negative, and 2 complex, and the total is 4. How about 0 positive, 0 negative? That leaves us with 4 complex. That's also a possibility. Okay, so these are all possible combinations of different types of zeros for that polynomial. And we won't know until we either, number 1, graph it, or number 2, list all possible zeros, try them, factor this polynomial, and get all of those zeros.